another device, and it's not going to be too much slower. So if I override device here, if I override device equals CPU, then we'll still print CUDA, of course, but now we're actually using CPU. 1, 2, 3, 4, 5, 6. Okay, about 6 seconds. And actually, we're not using torch compile and stuff like that, which will speed up everything a lot faster as well. But you can follow along even on the CPU, I think, to a decent extent. So that's a note on that. Okay, so I do want to loop around eventually into what it means to have different devices in PyTorch and what it is exactly that PyTorch does in the background for you when you do something like module.to device, or where you take a torch tensor and do a .to device, and what exactly happens and how that works. But for now, I'd like to get to training, and I'd like to start training the model. And for now, let's just say the device makes code go fast. And let's go into how we can actually train the model. So to train the model, we're going to need some data set. And for me, the best debugging, simplest data set that I like to use is the Tiny Shakespeare data set. And it's available at this URL, so you can wget it, or you can just search Tiny Shakespeare dataset. And so I have it in my file system as just lsinput.txt. So I already downloaded it. And here I'm reading the data set, getting the first 1,000 characters, and printing the first 100. Now remember that GPT-2 has roughly a compression ratio, the tokenizer, characters and printing the first 100. Now remember that GPT-2 has roughly a compression ratio, the tokenizer has a compression ratio of roughly 3 to 1. So 1,000 characters is roughly 300 tokens here that will come out of this in the slice that we're currently getting. So this is the first few characters. And if you want to get a few more statistics on this, we can do word count on input.txt. So we can see that this is 40,000 lines, about 200,000 words in this data set, and about 1 million bytes in this file. And knowing that this file is only ASCII characters, there's no crazy Unicode here as far as I know. And so every ASCII character is encoded with 1 byte. And so this is the same number, roughly 1 million characters inside this data set. So that's the data set size. By default, very small and minimal data set for debugging to get us off the ground. In order to tokenize this data set, we're going to get tick token encoding for GPT-2, encode the data, the first 1,000 characters, and then I'm only going to print the first 24 tokens. So these are the tokens as a list of integers. And if you can read GPT-2 tokens, you will see that 198 here, you'll recognize that as the slashing character. So that is a new line. And then here, for example, we have 2 new lines, so that's 198 twice here. So this is just a tokenization of the first 24 tokens. So what we want to do now is we want to actually process these token sequences and feed them into a transformer. And in particular, we want to rearrange these tokens and cannot be larger than the maximum sequence length. And then we have these T-long sequences of tokens, and we have B independent examples of sequences. So how can we create a B by T tensor that we can feed into the forward out of these one-dimensional sequences? So here's my favorite way to achieve this. So if we take torch and then we create a tensor object out of this list of integers and just the first 24 tokens, my favorite way to do this is basically you do a dot view of for example, 4 by 6, which multiply to 24. And so it's just a two-dimensional rearrangement of these tokens. And you'll notice that when you view this one-dimensional sequence as two-dimensional 4 by 6 here, the first 6 tokens up to here end up being the first row, the next 6 tokens here end up being the second row, and so on. And so basically, it's just going to stack up every 6 tokens in this case as independent rows, and it creates a batch of tokens in this case. And so, for example, if we are token 25, in the transformer, when we feed this in and this becomes the IDX, this token is going to try to predict that 198 comes next. So in this way, we are able to create this 2-dimensional batch. That's quite nice. Now, in terms of the label that we're going to need for the target to calculate the loss function, how do we get that? Well, we could write some code inside the forward pass because we know that the next token in a sequence, which is the label, is just to the right of us. But you'll notice that actually for this token at the very end, 13, we don't actually have the next correct token because we didn't load it. So we actually didn't get enough information here. So I'll show you my favorite way of basically getting these batches. And I like to personally have not just the input to the transformer, which I like to call X, but I also like to create the labels tensor, which is of the exact same size as X, but contains the targets at every single position. And so here's the way that I like to do that. I like to make sure that I fetch +1 token, because we need the ground truth for the very last token, for 13. And then when we're creating the input, we take everything up to the last token, not including, and view it as 4 by 6. And when we're creating the targets, we do the buffer, but starting at index 1, not index 0. So we're skipping the first element, and we view it in the exact same size. And then when I print this, here's what happens, where we see that basically, as an example for this token 25, its target was 198, and that's now just stored at the exact same position in the target tensor, which is 198. And also, this last token 13 now has its label, which is 198, and that's just because we loaded this +1 here. So basically, this is the way I like to do it. You take long sequences, you view them in 2-dimensional terms so that you get batches of time, and then we make sure to load 1 additional token. So we basically load a buffer of tokens of b times t plus 1, and then we sort of offset things and view them. And then we have 2 tensors. One of them is the input to the transformer, and the other exactly is the labels. And so let's now reorganize this code. And create a very simple data loader object that tries to basically load these tokens and feed them to the transformer and calculate the loss. Okay, so I've reshuffled the code here accordingly. So as you can see here, I'm temporarily overriding to run on CPU and importing the token, and all of this should look familiar. We're loading 1,000 characters. I'm setting BT to just be 4 and 32 right now, just because we're debugging. We just want to have a single batch that's very small. And all of this should now look familiar and follows what we did on the right. And then here we create the model and get the logits. And so here, as you see, I already ran this, only runs in a few seconds. But because we have a batch of 4 by 32, our logits are now of size 4 by 32 by 50,257. So those are the logits for what comes next at every position. And now we have the labels, which are stored in Y. So now is the time to calculate the loss, and then do the backward pass, and then do the optimization. So let's first calculate the loss. Okay, so to calculate the loss, we're going to adjust the forward function of this NN module in the model. And in particular, we're not just going to be returning logits, but also we're going to return the loss. And we're going to not just pass in the input indices, but also the targets in Y. And now we will print not logits.shape anymore. We're actually going to print the loss function. And then sys.exit of 0 so that we skip some of the sampling logic. So now let's swing up to the forward function, which gets sampling logic. So now let's swing up to the forward of 0 so that we skip some of the sampling logic. So now let's swing, then sys.exit, print not logits.shape anymore. We're actually going to print the loss function. And then sys.exit of 0 so that we skip some of the sampling logic. So now let's swing up to the forward function, which gets called there, because now we also have these optional targets. Sampling logic. So now let's swing up to the forward function, which gets loads.shape anymore. We're going to actually, and now we will print not loads.shape anymore. We're actually going to print the loss function, and then sys.exit of 0 so that we skip some of the sampling logic. So now let's swing up to the forward function, which gets called there, because now we also have these optional targets. And when we get the targets, we can also calculate the loss. And remember that we want to basically return logist loss, and loss by default is none, but let's put this here. If targets is loss, and loss by default is none, remember that we want, and when we get the target, because now we also have these optional targets. And when we get the targets, we can also calculate the loss. And remember that we want to basically return logist loss, and loss by default is none. But let's put this here. If let's put this here. If targets is not none, then we want to calculate the loss. And Copilot is already getting excited here and calculating the what looks to be correct loss. It is using the cross entropy loss as is documented here. So this is a function in PyTorch under is documented to be correct loss. It is using the cross entropy loss as is documented here. So this is a function in PyTorch under the functional. Now, what is actually happening here, because it looks a little bit scary, basically the f cross entropy does not like multidimensional inputs. It can't take a b by t by vocab size. So what's happening here is that we are flattening out this three-dimensional tensor into just 2 dimensions. the first dimension is going to be calculated automatically, and it's going to be b times t, and then the last dimension is vocab size. So basically this is flattening out this three-dimensional tensor of logits to just be two-dimensional b times t, all individual examples, and vocab size on in terms of the length of each row. And then it's also flattening out the targets, which are also two-dimensional at this stage, but we're going to just flatten them out, so they're just a single tensor of b times t. And this can then pass into cross-entropy to calculate a loss, which we return. So this should basically, at this point, run, because it's not too complicated. So let's run it, and let's see if we should be printing the loss. And here we see that we printed 11, roughly. And so, and notice that this is the tensor of a single element, which is this number 11. Now, we also want to be able to calculate a reasonable kind of starting point for a randomly initialized network. So we covered this in previous videos, but our vocabulary size is 50,257. At initialization of the network, you would hope that every vocab element is getting roughly a uniform probability, so that we're not favoring at initialization any token way too much. We're not confidently wrong at initialization. So what we're hoping is that the probability of any arbitrary token is roughly 1 over 50,257. And now we can sanity check the loss, because remember that the cross-entropy loss is just basically the negative log likelihood. So if we now take this probability and we take it through the natural logarithm, and then we do the negative, that is the loss we expect at initialization. And we covered this in previous videos. So I would expect something around 10.82, and we're seeing something around 11. So it's not way off. This is roughly the probability I expect at initialization. So that tells me that at initialization, our probability distribution is roughly diffuse. It's a good starting point, and we can now perform the optimization and tell the network which elements should follow correctly in what order. So at this point, we can do a loss.backward, calculate the gradients, and do an optimization. So let's get to that. Okay, so let's do the optimization now. So here we have the loss. This is how we get the loss. But now basically we want a little for loop here. So optimization now. So here we have the loss. This is how we get the loss. But now basically we want a little for loop here. So for I in range, let's do 50 steps or something like that. Let's create an optimizer object in PyTorch. And so here we are using the atom optimizer, which is an alternative to the stochastic gradient descent optimizer, SGD, that we were using. So SGD is a lot simpler. Atom is a bit more involved. And I actually specifically like the Atom W variation because, in my opinion, it kind of just like fixes a bug. So Atom W is a bug fix of Atom, is what I would say. When we go to the documentation for Atom W, oh my gosh, we see that it takes a bunch of hyperparameters, and it's a little bit more complicated than the SGD we were looking at before. Because in addition to basically updating the parameters with the gradient scaled by the learning rate, it keeps these buffers around, and it keeps two buffers, the M and the V, which it calls the first and the second moment. So something that looks a bit like momentum and something that looks a bit like RMS prop, if you're familiar with it. But you don't have to be. It's just kind of like a normalization that happens on each gradient element individually and speeds up the optimization, especially for language models. But I'm not going to go into the detail right here. We're going to treat it as a bit of a black box, and it just optimizes the objective faster than SGD, which is what we've seen in the previous lectures. So let's use it as a black box in our case. Create the optimizer object, and then go through the optimization. The first thing to always make sure the Copilot did not forget to zero the gradients. So always remember that you have to start with a zero gradient. Then when you get your loss and you do a dot backward adds to gradients. So it deposits gradients. It always does a plus equals on whatever the gradients are, which is why you must set them to zero. So this accumulates the gradient from this loss, and then we call the step function on the optimizer to update the parameters and to decrease the loss. And then we print the step and the loss. Dot item is used here because loss is a tensor with a single element. Dot item will actually convert that to a single float, and this float will live on the CPU. So this gets to some of the internals again of the devices, but loss is a tensor with a single element, and it lives on GPU for me because I'm using GPUs. When you call dot item, PyTorch behind the scenes will take that one-dimensional tensor, ship it back to the CPU memory, and convert it into a float that we can just print. So this is the optimization, and this should probably just work. Let's see what happens. Actually, sorry, let me, instead of using CPU override, let me delete that so that this is a bit faster for me and it runs on CUDA. Oh, expected all tensors to be on the same device, but found at least two devices, CUDA 0 and CPU. So CUDA 0 is the 0th GPU, because I actually have 8 GPUs on this box. So the the 0th GPU in my box and CPU. And model we have moved to device, but when I was writing this code, I actually introduced a bug because buff we never moved to device. And you have to be careful because you can't just do buff.to of device. It's not stateful. It doesn't convert it to be a device. It instead returns pointer to a new memory, which is on the device. So you see how we can just do model that to a device? That does not apply to tensors. You have to do buff equals buff.to device. And then this should work okay. So what do we expect to see? We expect to see a reasonable loss in the beginning, and then we continue to optimize just to single batch. And so we want to see that we can overfit this single batch. We can crush this little batch, and we can perfectly predict the indices on just this little batch. And in these, that is roughly what we're seeing here. So we started off at roughly 10.82, 11 in this case. And then as we continue optimizing on this single batch without loading new examples, we are making sure that we can overfit a single batch, and we are getting to very, very low loss. So the transformer is memorizing this single individual batch. And one more thing I didn't mention is the learning rate here is 3e-4, which is a pretty good default for most optimizations that you want to run at a very early debugging stage. So this is our simple inner loop, and we are overfitting a single batch, and this looks good. So now what comes next is we don't just want to overfit a single batch, we actually want to do an optimization. So we actually need to iterate these XY batches and create a little data loader that makes sure that we're always getting a fresh batch and that we're actually optimizing a reasonable objective. So let's do that next. Okay, so this is what I came up with, and I wrote a little data loader light. So what this data loader does is we're importing the token up here. reading the entire text file from this single input.txt, tokenizing it, and then we're just printing the number of tokens in total and the number of batches in a single epoch of iterating over this dataset. So how many unique batches do we output before we loop back around to the beginning of the document and start reading it again? So we start off at position 0, and then we simply walk the document in batches of b times t. So we take chunks of b times t and then always advance by b times t. And it's important to note that we're always advancing our position by exactly b times t. But when we're fetching the tokens, we're actually fetching from current position to b times t plus 1. And we need that plus 1 because, remember, we need the target token for the last token in the current batch. And so that way we can do the xy exactly as we did it before. And if we are to run out of data, we'll just loop back around to 0. So this is one way to write a very, very simple data loader that simply just goes through the file in chunks and is good enough for us for current purposes. And we're going to complexify it later. And now we'd like to come back around here and we'd like to actually use our data loader. So the import tick token has moved up, and actually all of this is now useless. So instead we just want a train loader. For the training data, and we want to use the same hyperparameters for 4. So batch size was 4 and time was 32. And then here we need to get the xy for the current batch. So let's see if Copilot gets. That's it, because this is simple enough. So we call the next batch, and then we make sure that we have to move our tensors from CPU to the device. So here, when I converted the tokens, notice that I didn't actually move these tokens to the GPU. I left them on the CPU, which is the default. And that's just because I'm trying not to waste too much memory on the GPU. In this case, this is a tiny data set and it would fit, but it's fine to just ship it to GPU right now for our purposes right now. So we get the next batch, we keep the data loader simple CPU class, and then here we actually ship it to the GPU and do all the computation. And let's see if this runs. So Python train GPT. .py. And what do we expect to see before this actually happens? What we expect to see is now we're actually getting the next batch. So we expect to not overfit a single batch. And so I expect our loss to come down, but not too much. And that's because I still expect it to come down because in the 50,257 tokens, many of those tokens never occur in our dataset. So there's some very easy gains to be made here in the optimization by, for example, taking the biases of all the logits that never occur and driving them to negative infinity. And that would basically it's just that all of these crazy Unicodes or different languages, those tokens never occur, so their probability should be very low. And so the gains that we should be seeing are along the lines of basically deleting the usage of tokens that never occur. That's probably most of the loss gain that we're going to see at this scale right now. But we shouldn't come to a zero because we are only doing 50 iterations, and I don't think that's enough to do an epoch right now. So let's see what we got. We have 338 thousand tokens, which makes sense with our 3-to-1 compression ratio because there are 1 million characters. So one epoch with the current setting of B and T will take 2,600 batches. And we're only doing 50 batches of optimization in here. So we start off in a familiar territory, as expected, and then we seem to come down to about 6.6. So basically, things seem to be working okay right now with respect to our expectations. So that's good. Okay, next, I want to actually fix a bug that we have in our code. It's not a major bug, but it is a bug with respect to how GPT-2 training should. happen. It's not a major bug. Okay, next, I want to actually okay right now with respect to our expectations. So that's good.